All right, so let's go ahead and get started. So let me start by talking about the ODPs. And I have my own version of the server here. So here's the README for ODP 201. We looked at this briefly yesterday. So basically, this is like a hello world, just to give you practice using the assess command. You're writing a function named sum, takes two integers, returns the sum of them as an integer. And you're going to put that into its own file, typically sum.c, but you can call it anything you want. Sum.c is not magic. Your responsibility in this assignment is to create that function. Okay? You're not required to create a main program. You're creating a piece of code that can be called by something called a test bed. Okay, a piece of code that I'm providing you, which is going to call your sum function and test it. Okay, the test bed is this /temp/main.o. But to test the sum function yourself, first thing you want to do is write your own main program. Right, call sum 5, 7, print out the result, make sure it's 12 or whatever. And as these functions get more complex, your test program is going to get more complex because you want to make sure the function is working correctly before you try to get it graded. So you've done that, or you've written your code and you really believe it works and you're ready to test it using the assessment system. Okay, I supply the main program. Okay, that's what /temp/main.o is. You're supplying the function, which in this case is in a file called sum.c. So to build an executable program which can be used for assessment, you can use a command like this, right? Compile, call the output program main. Here's the main program that I'm supplying. Here's the function that you're supplying. So if you do that, right, now I've got a program main in here that I can assess. Don't try to run main. If I try to run main, I'll get a seg fault, right? That's not a problem with your sum.c necessarily. You're not supposed to be running this main program. Main is supposed to be used for assessment, but you don't know what this main program is because I wrote it and I didn't give you the source code. Okay? Your goal is to create the sum.c, test it yourself with your own main program, and then link it with the test bed like we just did, and then assess that main program. So to assess, you say assess and then the name of the executable program that you've built. And you also need to specify the name of the source code file, sum.c, as a second argument. All right, so you do that, it brings you into the assessment system. And you've only got 3 commands you can use in here. Grade my assignment, exit the assessment system, or give me help. And the help is very unsatisfying because it's just those 3 commands. And help is one of them. So you really only got 2 commands, and one of them ends. So it's 1 command, submit. Okay, before you do anything else, take a look at this. It will always tell you what you're about to assess for. And if this is not what you think your function is supposed to be doing, you're confused, right? So maybe you've written ODP 202, which says, you know, implement a web browser, and you're going to assess it, and it says this should be assessing a function to receive 2 integers and return their sum. That's not what I did, right? Exit out. Don't say grade, because if you say grade and you've got the wrong code, you're going to get a 0 out of 10. And if you already did the correct code yesterday and got 10 out of 10, well, now it's changing to a 0 out of 10, right? So always look at that thing that you're about to assess your code for and make sure it's correct. Okay, in this case it is correct, so we can go ahead, we can use our G command. It tells me I got 10 out of 10 on every test. I'm good to go. Just go ahead and exit out, and you're done. Now let's say I messed up my sum function because I accidentally multiplied my numbers instead of adding them. So I build my test bed, I do my assess, I say grade, and I got 0 out of 10 on most of my tests. I lucked out and got 10 out of 10 on one, probably because I was adding 0 and 0. But the other ones, you know, so now I've got 10 out of 50 for this assignment. So exit out of that, Go back in, fix your code. Oh yeah, I'm supposed to add them. Recompile, reassess, regrade. There's my 10 out of 10 5 times. I'm good, I'm happy. Exit out, you're done. Okay, there's no magic in here. Right, I can call my executable haha if I want, as long as I say assess haha and my source code. And when I grade it, I'll still get 10 out of 10. I could call sum.c something totally different and compile that into the test bed and use that different name as the source code for that second argument on assess, and it'll still do exactly the same thing. But it's really easy. For example, if you have some main program that you did last week, and this time you say gcc/temp/main.o sum.c, it compiles fine, and now I say assess main sum.c. Well, what's going to go wrong here?
It's a.out, not b.
Yeah, when I say gcc/temp/main.o sum.c, my executable program that's created is called a.out, not main. So if I say assess main sum.c, who knows what I'm assessing? But it's definitely not this thing that I just compiled, and chances are I'm not going to get 10 out of 10. And this is where I start getting emails from people saying, here's my code, it looks perfect, but I'm getting 0 out of 10. And if I look at your code, yeah, your code is perfect, but you're getting 0 out of 10. Why? Because the problem wasn't with your code, the problem was with the way that you compiled it or that you assessed it. And probably about half the time when students are struggling with this and they're not getting 10 out of 10, it's not a problem with the code. It's a problem with the compilation or with the assess, or they're getting an error when they compile and they're ignoring it. And so they're continually testing the old version of main from the last time they didn't get a compile error, or things like that. So here's the deal. Write your function as required by the ODP, test the heck out of it with your own main programs, convince yourself it works, and then assess it, compile it with the test bed, assess it. If you're not getting 10 out of 10, look at your code, look at your test cases, make sure you've tested all the possibilities, make sure you're assessing correctly. If you do all that and you cannot figure it out, right, you can send me an email, but here's what I want you to do. Show me your function, okay, so that I can see exactly what's in there. If there's multiple functions, show me all of those. Show me your compilation, right? Your GCC line. Make sure I can see that. Show me how you ran the assess command. Show me the results of executing it. And now go back and grab all of this, copy it to your clipboard, paste it into an email message, send it to me. Okay? If you do that, there's a good chance I can look at what's going on and I can point you in the right direction. If you don't give me all of this, if I don't see this, I can't tell if you compiled it correctly or not. I can't tell if you got errors when you compiled it, right? If I don't see this, I don't know if you assessed with the actual name of the executable file that you created when you compiled. I don't know if your second argument was the correct name of your function, and so on and so forth, right? So I got to have all this information. If you come into my office and say, can you help me with this ODP, right, this is what we're going to do. You're going to show me your code, you're going to compile it, you're going to say assess, right? So if you can't get to my office and you're trying to get help over email, you got to give me the same experience. Does it make sense? Mm-hmm. Okay. So if some of this is missing, I'm going to shoot an email back at you and basically tell you, show me this, show me this, show me this. And we'll go from there. If you can't figure out how to make the function, right, go ahead and do a discussion. Right? I don't understand how we're supposed to add these two numbers. What is addition, right? Start a discussion in Canvas and somebody will explain it. All right, so questions on the ODP. About 2/3 of the class has already finished it, but it's due tomorrow morning at 8 o'clock.
You want us to put our name and relevant information in the source code.
You do not have to.
Okay.
You don't have to put comments in there because the grader doesn't care. But if it's something fairly complex, hopefully you're putting comments in anyway, and I can look at the entry. So let me just show you what we see here. So I get a grade file that basically shows me all the times that I asked for my work to be graded, and it's time stamped and the final grade is there. I also get a text file that shows me exactly what happened. So when a connection was made, what the file was, the contents of the source code file, and then what was generated by your program and what the correct program should have generated. So your program came up with 5 + 7 = 5. It should have been 5 + 7 = 12, and so on. So I can use this to help debug what's going on, but only if I have relevant information.
Question real quick about this ODP, because I noticed this.
Yeah,
Isn't this exactly the same as one we did in
probably.
this
It's a hello world basically.
So would it be considered plagiarism just to take our own code from that and just resend it because it's the exact same thing?
That's fine. Yeah.
Okay. Because this
And-
copying work
and-
is your own work, so.
And I mean that's the code right there, right? Which you can. Hmm? Yeah. So because the challenge here is not really the function. It's figuring out how to compile and link with the testbed and run the assess command. So yeah, you can reuse your code. All right. Any other questions on this? And there's a link at the top of the list of ODPs that points you to a 10-minute video that basically takes you through the same thing. And shows you these steps. All right, so I posted a link in Canvas up in the resources section that points to some lists of sample problems from 224. I've had some requests for ways to get back up to speed or refresh on C and programming. So if you feel like you've completely forgotten how to spell C and you want to go back and look at some practice problems, there's a page with some of those on it on Canvas now. I didn't mention explicitly yesterday in here, so I'll mention now. I am recording these lectures and posting them on Canvas, so everything that you see up here should be available by the end of the day, each day. 2:15 I'm not recording this quarter, but that's different. All right, any other questions on this? So let's jump into some data structure stuff. And later on this week, I'm going to go back and I'm going to start talking about some C programming. I'm going to talk about structures and type defs and arrays of structures. And I've had some requests for a refresher on makefiles and things like that. So we'll get to those in a few days. But right now I want to start talking about data structures, which is what this course is about. And I want to motivate our first data structure, which is something called a linked list. And I want to motivate it starting with the humble array, so integer x bracket 10. So x is an array. It's a chunk of memory that can hold 10 integers. And let's just suppose that the elements of x are as follows. Suppose we have 5 things in our array. And I'll throw some indices here. All right, so we've got 5 numbers stored in our array. They're not stored in any particular order. First thing we need to remember about arrays in C is that there's no inherent length to an array. there's nothing about X that tells the CPU that X contains up to 10 integers. So do you remember if I just use the variable X like in a print statement, if I pass the variable X to a function, what does X actually refer to?
Address.
Yeah, the address of
The first element.
the first element, right? So X actually refers to the location in memory where that 5 is stored. And that's it. That's all an array is. It's just a location in memory. So one consequence of that is there's nothing that we can do when we know the location where this 5 is stored to know how big this array is, right? If this is stored at location 100, there could be 5 elements in the array. There could be 5 million elements in the array. There's no way to tell. So usually when we have arrays of things like numbers, we also have to have something like a length variable. And in this case, I might say X's length is equal to 5, and that's my internal strategy for saying I've got 5 things in my array. And hopefully I know that I've allocated space for 10, so if I store more things and I increase X length, I won't let it get bigger than 9 or 10. But it's this artificial construct we have to just deal with because it's C. Languages like Java and such, this is taken care of for us. But for C, we got to deal with it ourselves. Okay, so we have a notion of length. So I want to look at operations we can do on arrays of numbers. So the first operation is searching. Suppose I want to search this array and see if some number is contained in it. So I give you this X, this beginning address of the array, and I say, tell me if the number 13 is in this array. How would you do that? What steps would you perform if you were a computer? Just sort of plain English description.
Look at the first element, then shift.
Yeah. That's really your only option, right? Look at the first element, see if that's the number we're looking for. If it is, you're lucky, you're done. I found my number in the list, right? If it's not, got to check the next number. Check the next number, check the next number. If I've checked enough numbers that I've gone through X length numbers and I haven't found my number, it's not in the list. If I'm looking for a 5, hey, I'm going to find it right away. If I'm looking for a 2, I'll find it after 3 operations. If I'm looking for a 22, it's going to take me 5 operations before I say, hey, it's not in the list. Okay, we're going to talk a lot in this course about efficiency of algorithms. How fast one algorithm is relative to another. Typically, speed's the thing we're concerned about, so how fast. And it doesn't really make sense to talk about things like milliseconds or microseconds. Those are artificial, right? I can take something that takes a millisecond to run on this machine, and I can put it on a different machine, and it might only take a microsecond. Or I can put it on a different machine, and it might take 10 seconds because it's a really slow mechanical computer, right? So the number of seconds that it takes, the amount of time, is not really what we're interested in. What we're usually interested in is more how many steps does it take. But even more than that, steps are artificial. If we're looking at assembly language, adding 2 numbers might take a lot of steps. If we're looking at Java, right, solving a quadratic equation might be a single step. So more than the number of steps or the amount of time, here's what we're interested in. When we're trying to do an algorithm on a set of data, if we increase the amount of data, how much more time does our algorithm take? So it takes a certain amount of time for this set of data. If we double the amount of data, what happens to the time? Does it double? Does it go up by 10%? Does it go up by 4x? Does it go up by 40x? How does the time increase when the size of the data increases? That's what we're mostly going to be thinking about. And this is something called order of complexity. And we have a symbol for this, which is just a script O. It's called big O notation. So script O, and we put something in here that basically tells us how the time grows as the data grows. Okay, so you said it doubles if we double the amount of data. That's exactly correct for this. If we have 5 things in our array, typically it's going to take us, 5 operations. On average, it might take 2.5, right? Because maybe we'll find our number in the beginning, maybe at the end, or maybe it's not in the list at all. But if we double this, if we have 10 numbers, right, worst case is going to go from 5 to 10. Average case is going to go from 2.5 to 5. If we have 1,000,000 times more numbers, it's going to take us roughly 1,000,000 times more operations. So it's linear. Double the data, double the time. Quadruple the data, quadruple the time. So the way we write linear growth, linear complexity, is we say order n. Because n is linear, right? As opposed to n squared.
Sorry, this is kind of a dumb thing, but I haven't seen before. So is script O, is that exactly what it looks like, or did you do it quickly because I don't know what it is?
Yeah, it's a script O.
I don't know what that means. It exactly looks like that.
So, yeah.
Okay.
So this means order of complexity n.
So it's the root from the out. Okay.
Yeah. Okay, order n is not very good because data grows really quickly. Right, look at Google. How many pages did they have to search through when they started? Right, a few. How many pages do they have to search through now? How many pages will they have to search through a year from now? Right, the size of
sand, how many grains of sand are there?
Yeah. That number grows fiercely, and if it took them, half a minute to search through their 100 web pages in the beginning, and now they've got 100 billion web pages, that's, 500 million minutes per search. So order n is not good compared to what it might be. Okay, let's look at another operation. Let's look at insert. Suppose I want to add some new number to this array of integers. Say I want to add the number 13 because I searched and it wasn't in there. Where should I store my 13? Do I want to store it here at element 0? Probably not, because I'm going to wipe out my 5. I can't store it in element 1 because I'll wipe out my 10. So where should I store my 13?
6.
How about storing it right here? Right, because that location is unused. My x length is 5, so I know I only have 1, 2, 3, 4, 5 things in my array. The next entry in my array is free. Well, how do I find the next entry in my array? It's index 5. Well, that's what x length is. This is the funny thing that arrays do, right? If x length is 5, I've got 5 things in my array. The next open location is element x length. So I take my 13, I store it here, and then what do I have to do? One more thing. Got to increment x length. Otherwise, the next thing I store will overwrite my 13. Well, now my x length is equal to 6. And if I want to store something else, it's going to go right in element 6. So how many operations is it taking to store something in this array?
2.
2, right? Basically, write your number into the index location given by x length and then increment x length. Does it matter how big my array is to begin with?
No.
If I have 1,000,000 things in here and x length is 1,000,000 and I want to insert something new, it's still the same 2 operations, right? So this is constant time. So we say this has order of complexity 1. And that's almost your ideal. It means no matter how big your data is, it always takes the same amount of time to do your operation. I think order 0 would be the ideal, where it takes no time. All right, so insert is pretty efficient. And what about delete? Suppose I want to delete the 14. How might I do that? What sorts of steps might I have to do?
You'd have to remove the 14.
Okay.
Then you would have to shift all the remaining elements lengths up.
So I remove the 14, I put the 6 up there, I put the 13 up here, and I set X length to 5. So that'll delete. What's the order of complexity of that?
4?
In that case, it was 4 operations. What if I deleted the 5, though?
Now 6 or 7?
It's bigger, yeah. I have to shift everything up. So yes, who said n? Yeah, so this is order n, right?
Ew.
Yeah. There's a trick, though, we can use for deletion in this case. We can do this in order 1. Remember, the order of these numbers in the array doesn't matter.
We haven't skipped 14?
Effectively,
You could take the last number and put it in where you deleted it.
cool. So let's take this 14 and let's replace it with the last number and then decrement X length. And now what's in my array? Well, there's a 5, 10, 2, 13, and 6. And that's it. There's another 13 here, but since I'm saying there's only 5 things in the array, this is irrelevant. And that'll bring us back to an order 1. All right, so arrays can be very efficient for inserting and deleting as long as the order of these things in the array is irrelevant. We just want to store a bunch of numbers in this chunk of memory called an array. We don't care what order they're in. Very efficient to insert and delete. Search is expensive, though. And of course, to delete something, you've got to find it first, so you have to do a search in the beginning, and so on. But the delete itself and the insert itself are efficient. Okay, how do we speed up search in an array? What can we do so that we don't have to take n operations to tell if a number is in our array or not?
Well, if the array is sorted already,
Okay, if the array is sorted, what can we do?
then you can directly jump to the range that you want to look for.
Yeah. So you actually did this in 224 when you wrote a high-low game. High-low is what we call a binary search. And effectively, a person is thinking of a number, you're searching for that number in a list of numbers from, say, 1 to 100. Right? So you're thinking of the number 79. So what do? You pick a number in the middle, 50. And since this is sorted, we can say 50 is too small. We don't have to check anything in the array that comes before 50. Right? So here's what we basically do. We're looking for, so let me miraculously sort our list of numbers. So here's a 2, 5, 6, 10, and 13. So you're looking for the number 10, right? Start right in the middle of your array. Look at the 6. If the 6 is too small, we know that your number can only be in this lower half of the array. And now we've done one operation, but we've shrunk our problem from dealing with n things to dealing with n over 2 things. And with one more operation, we'll shrink from n over 2 to n over 4. And we keep doing this until the array that we're searching contains a single number, and it takes one operation to check an array containing one number, and it's either our number or it's not in the array. So if we sort, so this is unsorted. If we sort, this will turn out to be order of log n, which is really nice efficiency. It means if you have 1 billion times more data, it takes you 30 more steps. 30 times as long, as opposed to 1 billion times as long. Right? 30 microseconds instead of 1 microsecond, not a big deal. Okay, 1 billion microseconds as opposed to 1 microsecond, very big deal. So order of log n is nice. Yeah.
But that's with numbers. What about like you say Google? How would they use this?
Same idea. No, Google search is a whole can of worms, right? But you can still analyze complexity this way, right? And look at how time increases with data size increase. But they're doing all kinds of things with associative maps, some of which we'll talk about, and using data structures like search trees and stuff, which we'll talk about, and they have their secret sauce, which nobody talks about, and stuff like that. But similar principle. All right, well, if our data is sorted, search becomes very efficient. What happens to insert, though? Right, so now we've got a scenario like what Connor suggested, which is if we want to insert something between 5 and 2, we're going to have to move everything down to make space for it. Right, so if we want to...
Insert it at the end and sort it again.
But sorting is expensive too. So if we want to insert a 3, we can put it at the end and then sort. And if we do a bubble sort, that's order n squared, which is not good. Or we could move everything down to make space and then put our new number in that open spot. And so this becomes order n, and delete will also become order n, because when we delete something, we have to basically move things up to fill in that thing that we deleted. So sorting our data helps us a lot with search, but it kills our performance with insert and delete. Okay, so what we want to do is we want to look at a way to do more efficient insert and delete on an already sorted array. We want to be able to insert and delete in order 1 without disturbing the sort order. And this is not going to help us with search. We're going to find out our search is still going to be order n when we're done. But 3 or 4 weeks from now, we'll address that and we'll bring the search time down to log n again. But right now, we're just thinking about insert and delete. But the question is, how do we insert or delete to or from an array in order 1, but still keep the thing sorted? So efficient insert and delete on a sorted array. So that's our current goal. And with an array, there's really no good way to do that. Because the way arrays work, the reason arrays work in C is because if we know the location of the first element, we can find the location of any other element using a simple formula. So suppose x is equal to 100. So memory location 100 contains x0. If this is an array of integers, integers take 4 bytes. So element 1 of the array is at location 104. Element 2 of the array is at location 108. Element 3 is at location 112, and so on. And in general, element I is at location 100 plus 4 times I. So when we pass x to a function, all we pass is this number 100. The compiler has written code based on the fact that this is an array of integers, so when you access x bracket I, the code the compiler made for you just says go to memory location 100 plus 4 times I. And it takes that value of I, multiplies by 4, adds 100, goes to that spot in memory. That's element x bracket I. So there's this very tight connection between each element of your array and a predefined location in memory based on where it starts. And if this is the number 5, and this is 10, and this is 20, and this is 23, and we want to insert a 7, we really want it to go in between here and here. There's no space. Right? This is an integer. It takes locations 100, 101, 102, 103. And this next number starts at location 104. Where the heck are we going to put that 7? There's no physical memory between this element and this element. So we've got to do a trick. And the purpose of this trick is to break this connection between elements of our array and locations in memory. Well, how do we do that? Very simply, instead of just having our numbers, we're going to have 2 pieces of information for each element in our array. We're going to have the actual number we're storing, but we're also going to have something that tells us where the next element of the array is. We're going to have some kind of arrow, pointer. He said it, not me. I'm not going to say pointer for a while, but it is a pointer. We're going to have some kind of arrow that points to the next piece of our array. And we're not going to assume if this is location 100 that this is necessarily location 104. This could be location 520, all right? But there'll be something here which says, hey, in the next piece of the array is location 520. And this last piece of data should point to wherever the next thing in the array is. Well, if it's the end of the array, there's nowhere for this to point, so we'll put a special pointer in here. We'll just call it null for now. And null is just a flag saying there's nothing else after this piece of data. And we're going to call these things nodes. So a node is a 2-part piece of data. It's got the actual number that we're storing in the array, but also something like an arrow that tells us where the next piece of data is in our array. Okay, what does this do for us? Suppose this is our array and we want to insert the number 7. Well, we're going to create a new node. We're going to store a 7 in the data piece of that node. But right now, if we look at our array of numbers, it's got a 5, a 10, a 20, a 23. There's no 7 in there. How do we get the 7 to be part of this list of numbers?
You redirect a pointer.
Okay. So you still have to find where, you still have to do a search to figure out where you want it to go, but we searched and we know we want it to go between the 5 and the 10. Okay, after the 5, before the 10. Here's what we do. See what the 5 is pointing to? Make your 7 point to the same place. That's one operation. And then take your 5 and have it point to your new node. 2 operations we've inserted into the middle of this list. And now if we look at the list, it's a 5 followed by a 7, 10, 20, 23. It's still sorted. All right, let's delete 20. Well, how do we delete the 20? What do we have to do to this picture? Yeah. To delete the 20, all we got to do is change this to point to the 23. Bingo, we're done. 20 is no longer part of the list. Now our list contains a 5, a 7, a 10, and a 23.
You still have to follow the chains to get to the 21st, though, and find it before you...
Yes, you still have to find it, which you do by following the chain. So that's order n.
Yeah.
And that's what we'll fix when we get to trees.
So in this case, you can just leave the arrow from 20 to 23 because it's not 20's never.
Yeah, 20 is still pointing to 23, which seems a little weird, right? But there's nothing pointing to 20 anymore, so it doesn't do any harm. And always keep in mind, you know, there's a box here somewhere in memory. It's got stuff in it. There's actually no such thing as an empty location in memory in most computers. There's something in there. And if we think, what is the value of this integer here? It's got some value. Right? These are these crazy negative 2 billion numbers that you see when you forget to initialize things and you print them out. right? So there's something in there, and in this case, yeah, there's some block here that's pointing to this 23, but there's probably other blocks that are pointing to things. But as long as we don't stumble across this 20, that's not a problem. All right, so this is a linked list. And we need some way to know where the first thing is, because this may not be, the location 100 where our array actually begins. So we've got to have something, I'll call it a header for now, that tells us where the first thing in our list is. But once we're at that first thing, we can keep following these pointers to get to the next things until we get to something that points to null, and that's the end of the list. So this is kind of like an array, but we can insert and delete in the middle without changing the order of things very efficiently once we know where to insert or delete. So this is called a linked list, and this is what we're going to spend the next few weeks playing with. And your first programming assignment, PA1, is basically going to be implementing a linked list in C. And your second programming assignment, PA2, is going to be implementing a linked list in C. And everything is going to be exactly the same for PA1 and PA2, except how you do the implementation. So in PA2, we're going to talk about pointers, and we're going to use ampersands and stars and mallocs and freeze, and we'll get lots of seg faults and all kinds of good stuff like that. In PA1, we're not. PA1, we're just going to use arrays and structures. And we're going to use a bit of a cheat to make all this work. So here's what it's going to look like, and we're going to talk about structures in detail tomorrow, and we'll go through PA1 in detail tomorrow. But here's the basic idea. We're going to make an array of structures. So a structure for now, just remember, it's something that has multiple pieces to it. So an array of structures looks like this. It's an array. It's got indexes. And I'm going to give each element of this array 3 fields. I'm going to call this first field data. I'm going to call the second field next. And I'm going to call this third field valid. And I'm going to have a variable called header. And let me put together a list. Let me 5, 10, 20, 23. Okay, suppose this is what my array looks like. It's got a bunch of entries. The first 4 entries look like I've described. The valid flag has a check mark to say it's valid and X to say it's not valid. Same marks I use on exams. So what does this look like? Header is equal to 0. It tells me my first node is stored at location 0 in my array. Well, it's a block that has a data value of 5. And the arrow that points to the next block contains a 1. That means it's pointing to the block stored at index 1 in this array. So index 1 is a 10, index 2 is a 20, index 3 is a 23. So block 5 should point to this block containing a 10. That's that arrow. That should point to the block containing a 20, which should point to the block containing a 23, which doesn't point to anything. It's the end of the list. And our header points here. Okay, so suppose we want to delete the 20. What do we do with our picture? We take this and we just skip over the 20 and point to the 23. So how do we do that in our array? We take the node 10, and instead of pointing to the 20, we point to the thing that 20 pointed to. We're deleting 20. 20 was followed by index 3. So we take the previous node, and we just change that to a 3, and we're done. We're skipping over that 20 now when we go through our list. Now if we ask our code what's in the list, it's going to say header is 0. So we've got a 5, followed by a 10, followed by a 23, and that's it.
Is 2 still valid even though it's not pointed to?
So the other thing I want to do is I want to change this valid flag.
Oh.
And it doesn't affect what's in the list, but if we don't do that, our code's going to think that this is meaningful, and we're going to run out of space more quickly. So we're going to clear that valid flag. Okay, so what does that do for us? Well, suppose now we want to insert a 7. Well, we need to make a new block somewhere, but in fact, this element 2 here is not being used for anything, right? That's this block right here. So we can take this, we can change this to a 7, and it's got to go in between the 5 and the 10. So wherever the 5 is pointing, we're going to change this new block to point there. And then we're going to change the 5 to point to our new block. So how does that affect the array? Well, we took our block that was not in use, element 2. We set the data value to 7. We changed it to point where the 5 was pointing. 5 was pointing to 1. So we'll change this to point to 1. And we'll change 5 to point to this new block, 2. And we'll go ahead and we'll mark this valid. Okay, so now we ask our code what's in our list. Header is 0, contains a 5, followed by 7, followed by 10, followed by 23, and that's the end of the list. And all our data's in there, and it's all sorted, and we actually reused this block that we had deleted earlier. Okay, this is all there is to linked lists, right? So you're going to be drawing pictures like this, and you're going to be making maps of arrays like that, and you're going to be trying to do things to your picture of blocks with arrows, and you're going to figure out what needs to happen to the array, and then you're going to write code to do it. Okay? So the programming assignment, the gist of it is writing a bunch of code, but that's not the important part, right? And PA1, PA2, the code's going to look fairly different from each other. If you do this in Java, it's going to look completely different. What's important here is this, right? That's the most important part. The second most important part is this. Yeah?
Is there a specific name for that type of chart, or is it just a chart?
This is an array, actually. It's kind of like a memory map,
Okay.
but memory map means a lot more than just that.
So on the test or something, you wouldn't say do a blank, you'll just say do it.
Do that thing I did on that first Tuesday
Okay, exactly.
for 100 points. No, I won't.
Okay.
Okay, so we'll look at PA1 in detail tomorrow, and we'll come back and we'll address this with specifics from the programming assignment. But this is the essence of linked lists, and it's your first full-on data structure in this course. But once we're comfortable with drawing pictures like this and turning this into code to do these manipulations, that's the whole course, right? When we do trees, the algorithms will be, hundreds of lines and whiteboard after whiteboard of manipulations, but it's the same stuff, right? So the goal in these first two assignments is to get really comfortable with this. And PA2 will look almost exactly like PA1 in the end. I had one student who actually changed PA1 into PA2 just by doing some global substitutes in VI, and they had PA2 working perfectly. Okay, so I'm setting them up to be very parallel on purpose, but we're doing it like this first to avoid the more yucky stuff. All right, so we'll continue from there tomorrow.
Question?
Yeah.
Should I go just email you?